Right, in just the previous video, we kind of took a quick look at the voltage and current relationship in capacitors and in inductors, and kind of intuitively figured out what we mean by the current either leading or lagging the voltage and why that happens with inductors and capacitors. And we did some measurements on the scope to kind of show those same principles. So this video we're going to take a quick look at what happens when we start combining inductors and capacitors in circuits, and some special things that happen particularly at resonance. So what is resonance? Resonance is essentially when the capacitive reactance, or 1 over 2 pi Fc, is equal to the inductive reactance in the circuit, okay, 2 pi Fl. And it also means that that's when the phase between the voltage and current is equal to 0, kind of like a resistive circuit. So let's take a look at what happens on paper here first, and we'll look at it on the scope. So let's consider, say, a series LC circuit first. A series LC circuit, okay, the current through the inductor and the capacitor are equal because they're in series. There's no other place for the current to go, so the current must be equal between the inductor and the capacitor. Okay, so if the current is equal, we know that there's a difference in the phase between the voltage across the inductor and the voltage across the capacitor, okay, with respect to current. So let's look at what the voltages do. So the inductive voltage, okay, is going to be set up such that the current is lagging the voltage, right? For an inductor, right? The current lags, okay, the voltage. So this would be the voltage across that inductor, okay? If we look at the voltage across the capacitor, it's just the opposite, okay, where the current is leading, okay, the voltage. Okay, see the peak of the current is occurring before the peak of the voltage. Okay, so this is the voltage across the capacitor. So if we look at the circuit, the total voltage across those, or if we redraw it, okay, the total voltage across the inductor or capacitor is just the sum of the inductor voltage and the capacitor voltage. So if we take the inductor voltage here and we add it kind of point by point to the capacitor voltage, we could see we wind up with 0, right? Because this is kind of positive, this is negative, and that would go to 0. Now, again, we're assuming we're at resonance. Okay, so at resonance, the inductive reactance and the capacitive reactance are equal, so the voltage is going to divide equally across them. Okay, so these are going to have the same magnitude. Okay, but because one was leading by 90 degrees and one's lagging by 90 degrees, these two voltages are 180 degrees out of phase, and they completely cancel each other out. So what that means is that for a series LC circuit, this looks like a short at resonance. Okay, so at low frequencies, okay, the circuit is going to look capacitive. At high frequencies, it's going to look inductive. But as you pass through the resonant frequency, the impedance of this overall circuit ideally goes to 0, okay, and essentially turns or shorts out. Okay, so that's kind of a unique property of a series LC circuit. And I've got that set up here on the breadboard. I've got my inductor right here. I've got my capacitor right there. They're in series. And if we look at what we're doing here is we're probing. Both the probes have to be referenced to ground. So one probe, channel 2, is going across the inductor. Channel 1 is actually going across the total sum of the two. But then in the scope I can do a little bit of math, subtract V1, or voltage of channel 1 minus channel 2, and that'll just give me the voltage across the capacitor. So what I'm looking at on the scope here, down here, that's the voltage across the inductor. That's the voltage across the capacitor. It's really the difference between channel 1 and channel 2. Okay, and if I change the frequency, okay, I reach up here, we'll see what happens is that as I go, in this case, higher and higher in frequency, the voltage across the capacitor is going down with respect to the voltage across the inductor. If I come back down in frequency, we can see the opposite occurring. The voltage across the capacitor is getting larger, voltage across the inductor is getting smaller. And notice that these signals are always 180 degrees out of phase, just like we showed right there. Okay, but now if we reach that special condition where both of those are equal to each other, okay, when you add them up, Okay, the total voltage across that series combination is actually going to be equal to 0. And we can see that by turning on channel 1, because channel 1 is probing that. Okay, so there's channel 1. That's essentially the sum of those two. It's the voltage across, that series combination. And you'll notice as I go below resonance, I get a voltage there. If I go above resonance, I get a voltage. It changes polarity, right? We go from inductive to capacitive and vice versa. Okay. Actually, I just said that backwards, but you get the idea. But then as you cross through resonance, you can see that the voltage essentially across this stack goes to 0 because it's essentially been shorted out because of the way these phases add up. So that's kind of what happens with a series inductive circuit, and very often used in tuned circuits. Okay, you can see how a frequency selective network like that could be really useful in things like oscillators and filters and things like that. Okay, so the other configuration is a parallel resonant circuit, okay, where you put the inductor capacitor in parallel. Now in the parallel inductive resonant circuit, or LC circuit, the voltage across them is the same because they're both connected to the same point. There's 0 ohms between them, so the voltage across them is going to be the same. So let's say that's the voltage across L and C. But now we can just, again, draw out what the currents are doing, right? Because the total current in this circuit is going to be the sum of the current going through the inductor and the current going through the capacitor. We add those two up, and that gives us the total current going through. So let's see what happens. So again, if we draw the inductive current, remember the inductive is lagging the voltage, okay? And we draw the capacitive current is leading the voltage. So we can now see these two currents are 180 degrees out of phase, and just like the voltages in the previous example, they add up to 0, okay? Ideally, okay? So the property now of a parallel LC circuit is when you cross through resonance, okay, there's going to be no current flow. IT is going to be no current, which means these two things essentially create a tank circuit that doesn't allow any current to flow through them. So it almost looks like an open circuit. Okay, so that's the property. A parallel LC circuit looks like an open circuit at resonance. Okay, so as we go lower frequency, the circuit's going to look more inductive. Okay, and at higher frequencies, the circuit's going to look more capacitive and tend to kind of, allow current to flow. But at resonance, those two currents cancel themselves out, and you wind up with essentially an open circuit. Okay, so we can configure this guy over here really quickly. What I'll do is I'll take channel 1, which is this guy right here. Let's pop this over here, and let me put my generator over there. Okay, if I bring this capacitor lead down and plug it into the breadboard here, it's tough to do while we're on camera. There we go. And let's just turn off all these other channels on the scope and just look at, well, now I'm looking essentially at this situation. I'm just probing directly across that combination. Okay, so now I see my voltage across there, and I'm still at resonance. If I go below resonance, I can see that voltage is going, or above resonance in frequency, I can see that voltage going down because it's loading the circuit more. If I come back up, the magnitude of the signal goes up. If I go above resonant now below resonant frequency, I can see that magnitude of the signal going down because we're drawing more current through the inductor, and here we're drawing current through the capacitor. But now right at resonance, we kind of peak in magnitude, okay, right there, because now we're essentially just looking at the open circuit voltage of my generator across this parallel LC circuit. So you can see some pretty powerful things that can happen here with series or parallel resonant circuits that allow you to create networks that will have either a short circuit or an open circuit at a particular frequency. And by playing with the values of L and C, you can create tuned circuits to create things like filters and other frequency selective networks. So it can really be handy in designing AC circuits. So I hope this was helpful in understanding what happens with LC circuits at resonance.